And let me toss you a quick reminder of what we did last time. Last time we were here, we took a vote about what would happen if we put a light bulb in barium hydroxide, a light bulb in HCl, a light bulb in H2SO4. Everybody pretty much knew that the BaOH2 would light up the bulb. Nobody thought that the HCl would light up, but it did, and it was real bright. And we were kind of on the fence about the H2SO4, but it lit up as well. So when all was said and done, it ended up that all of them lit the light bulb. The first one because it was ionic, the second one because it belonged to a new category of compounds that we call acids. And we took a little green piece of paper, we attached it to our resource sheet, and said that from this point forward, we just have to kind of be on the lookout for the acids. They're just compounds that look molecular, but give off a hydrogen when they're dissolved in water. So acids ended up being molecules that give up hydrogen when they dissolve in water, because they give up hydrogen ions that allows them to conduct an electric current. What I'd like you to do now is, on this sheet, using a pencil, just in case it doesn't go well, I would like you to draw 2 particles of each of these things into the beakers to explain why each one of them was able to conduct electricity. So this is definitely related to what we just did on your test about trying to show things that conduct electricity. Here we go. If you want to check your work, barium hydroxide is kind of old news. That's an ionic compound. We split off the barium ions. We split off the hydroxide ions, but we leave the hydroxides bundled together as hydroxide and add a little bit of water, spreading everything out. HCl, well, since this conducts electricity, we have to have some ions, so we need to have those charges. They need to be free to move around in the water, and so we get these 2 hydrogen ions and these 2 chloride ions free to move around. And then with our H2SO4, we break it apart into 2 hydrogen ions and 2 sulfate ions. And probably the easiest way to think in terms of how do you know which ions that thing's going to break into is to think about what you'd have to do to get this chemical formula. Sulfuric acid is the acid that's made from the sulfate ion. And if acids have to contain hydrogen, hydrogen is a +1. So we're back to that idea of the fill the box is going to help us figure out what parts and pieces it breaks into when it gets wet. So this breaks into 2 hydrogen ions that don't stay as H2 because they're both positively charged, so they repel one another. And so we end up with our sulfuric acid looking like that. Now, if we were to try to put all the things we've done together, we have a little bit of a problem. This accounts for the lighting up of the light bulb, and that's good. The problem is that we've been focusing on balancing equations, and particle level pictures of balanced equations are situations where the equation and the particles look like a good match. If we were to go forth and try to balance an equation with this mess, this would not go very well at all. This doesn't look anything like its chemical formula. And so if what we want to do is get the equation balanced, instead of explain why the light bulb is lighting up, what we need instead is a slightly different picture. The solution to our problem is actually going to come from children's literature. The Lift-A-Flap book. Hopefully you've all had one of these in your lifetime. We are going to start to do chemistry in a lift-a-flap sort of way. Okay? So like, Here's a tractor. I wonder what's underneath the hood. Oh, look, a powerful engine. Okay. So from far away, it just looks like a happy tractor. But if we zoom in and look a little more closely, the happy tractor has a powerful engine. I wonder what makes it go. Oh, if I look more closely, we have a gas tank. So what this picture is a look more closely picture. We want to be able to shut the flap on our picture to get it back to looking like it would be useful to balance a chemical equation. The other piece of this packet, if you look at the next page, is 3 beakers. I want you to take those 3 beakers and cut them out, and we are going to put on some flaps. Okay? So, yes, this is a craft. You're going to cut out the beakers, and you're going to put them over the top, and then there's some tape on your table, and you're going to tape them down. Now, some of you have the personality that says, I need to cut this beaker out so that it's exactly the shape of a beaker. That's awesome. Others of you have the personality that says, you know what, I'm going to cut this into roughly a rectangle and tape it down to my piece of paper. Well, we can't leave our lift-a-flap book like this, because in a lift-a-flap book, the flap has something on it and the flap has something under it. So we need to do the illustration for the top of our flap. The top of our flap is always going to be a more simple picture from backed up from farther away. So at a more simple level, 2 particles of barium hydroxide dissolved in water from a distance might look like exactly what it says it is. 2 particles of barium hydroxide dissolved in water. So there's 1. We decided we put 2 in each of our beakers. And then we need some water molecules. I'm going to peek under my flap and see how many I used. So I put the same amount on the top of the flap as the bottom flap. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I used 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Your top flap pictures look a lot like the chip models from Unit 1. There's not a lot of complexity to them, but they do represent the chemical formula. So from a distance, a solution of barium hydroxide is barium hydroxide particles in water. If we zoom in more closely, we find out that when barium hydroxide dissolves in water, it falls apart to make ions. If I want to explain why the light bulb lights up, this is a useful picture. If I want to know the chemical formula, or I want to use this to balance a chemical equation, my top flap is a more useful picture. Neither one is particularly better than the other. It's just different models for different purposes. From a distance, HCl in solution looks like that. Now I got to peek under so I can count my water molecules. I did 1, 2, 3, 4, 5, 6, 7. Yeah, that time I drew 7. 1, 2, 3, 4, 5, 6, 7. So from a distance, dissolved HCl looks like this. It's nice because the particle matches the chemical formula. But if I zoom in a little closer, I can explain why the light bulb lit up. And lastly, my H2SO4. From a top flap perspective, there's some H2SO4s. 1, 2, 3, 4, 5, 6, 7, 8, 9. From a distance, H2SO4 looks like that. And if I need to explain why the light bulb lit up, I just peek a little closer. Next week, we're going to be doing a lab, and we're going to be making a lift-a-flap book to describe the things that happened in lab. On the back side of this sheet, you will find descriptions here of our two types of particle level pictures. For lack of better terminology, we're going to borrow little kids' literature language, top flap and bottom flap pictures. Your top flap pictures are like the ones that we drew back in Unit 1. They go with our reaction 1 target. We don't show any charges. We don't break anything up in solution. We just make sure that we meet conservation of mass. It's most useful if you want to think about chemical formulas and if you want to think about balanced equations. Our bottom flap pictures are a lot more complex. They go with our matter 3 target. It's more like our Unit 2 pictures. We include charges on ions and ionic compounds. We break up those ionic compounds in the acids if they're dissolved or if they're aqueous, but we make sure that the conservation of mass is met. And these are the pictures that we need if we need to make a prediction about what's going to happen with our light bulb.